JASP contains a module that allows us to explore probability distributions. The module is here, but it's blurred, so it's not available. In order to make it available, we need to open data. So let's go to open data. We can do it by two ways. One is to go to data library and go to the category discover distributions. We go there and there is a data set that we can use. But we can also use any file that we want. So I just used one that I've used recently, and now the module distributions is available. Let's start with the normal distribution. Okay, so here we've got some parameters, and here is the graph that we would like to see. The parameters that JASP is using here is mu, which is the mean, and sigma square, which is the standard deviation. Sigma square is the variance, but it gives us the option to change to mu and sigma, which is the standard deviation. So here is showing the range from -3 to 2,3, but we can extend that to, let's say, -6 to 6. And obviously when the mu is 0 and sigma is 1, this is the standard normal distribution. But we can change that. We can have distributions with different mean and different standard deviations. So we can do that, but when we do that, there are some of the features that we want to explore that they are not going to be available, so I'm going to keep it like this. But if you want to explore, you can change those values, but make sure you change the range as well, because let's say if you if you put the mean to be 10 and the range of values of the variable x are from -6 to 6, then you are not going to see the proper distribution. So change the range of values accordingly. Okay, so let's go and see what we are interested in, which is to see what's the probability for different intervals. So we cannot say what's the probability. When we use probability, we say probability mass. We refer to probability mass of one specific value. In a continuous distribution, there is the probability for a specific value is 0. We cannot give a probability to a specific value. So we need to give a probability mass to an interval of values. What we can do is provide probability density for specific values, but probability density uses calculus, and what it does is to have very small intervals, calculating the probability mass of over that interval and dividing that by the length of the interval, and that gives us the probability density for that interval. But if that interval is so small, it's like equivalent to giving the probability to one specific value. We are going to explore the probabilities for intervals of values. So here in the standard normal distribution, when we take values from 0 to 1, the probability that the random variable takes the values from 0 to 1 is 34% or 0.34. And if we go -1 to 0, should be exactly the same because it's symmetrical. Okay, so we've got 34% there, and if we put -1 and 1, you saw while I was trying to get this one, it should be double of that, 68% or 0.68. We can use this feature, and tells us the interval that goes from -infinity to any value. In this case 0 should be 50%, and if we go the other way around, from 0 to +infinity, should also be 0.5 because it's a symmetrical distribution. Okay, so one typical interval that researchers are interested in is 1.96, and I'll show you why. Let's say 1.96 to 1.96. Enter. Okay, so these two values are important because within these two values we've got 95% of the probability. So the probability that the X random variable will take a value between negative 1.96 and 1.96 is 95%. So when we construct 95% confidence intervals, we are exploiting this characteristic of the normal distribution. Let's go to the student's t distribution. Now, the student's t distribution contains some of the characteristics that are also in the normal distribution. So one is that it's a symmetrical distribution. It's centered here in 0, but it could be centered in other values, but we're going to leave it there. And it's symmetrical. So it's symmetrical to, that means that the shape of the distribution is the same for both sides from the mean of the distribution. Now, for defining the student's t distribution, we need the parameter called degrees of freedom. df is degrees of freedom. And NCP is non-centrality parameter. We are going to leave it in 0, but you can change that as well. But we are going to concentrate in this value. So let's say we're going to put degrees of freedom in 10. And we are going to do the same as in the normal distribution. We are going to put the range of values from -6 to 6. Okay, so we've got that distribution, and as you can see, the two distributions are similar. And if we see probability, now between 0 and 1 is 33%. Remember that in the case of the normal distribution was 34%. So if we put from 0 to, let's do same as before, 1.96, negative 1.96 to 1.96. Okay, so instead of having 95% of the distribution between these two values, it has 92% of the distribution. What means here is that values that are further away from 0, negative or positive, are more likely in the t distribution than in the normal distribution. So when we have outliers, it's typically better to use a t distribution instead of a normal distribution, because this distribution takes into account those outliers. Now, when this is the degrees of freedom is 10, we've got this distribution. When we change that, it changes the distribution. So if we put less degrees of freedom, the percentage of the probability between minus 1.96 and 1.96, which will be even lower. So let's put degrees of freedom 5. Okay, so 0.89. But if we put 20, it will become similar to the normal distribution, 94. And if we get 30, still 94. And we got 95% of the population. So when we've got a degrees of freedom of 50, it's it's same as the normal distribution. So, but you saw that with 30, it's quite similar. It's 94%. So it's not exactly the same, but it's quite similar. So degrees of freedom is something that is, it's not an easy concept, but sometimes it's related to, when we do research, to the sample size. The Bernoulli distribution has the parameter pi, or p in this case 0.5, which is the probability of success. So this simply we are going to see that we have this distribution. This is a probability mass function because it's a discrete value, and we've got that the probability of failure, or 0, is 0.5, and the probability of success, or 1, is 0.5. Now, if we change this p to 0.6, then the graph here will change, and now the probability of success is 0.6 and the probability of failure is 0.4. It's a bit boring distribution, the Bernoulli distribution, quite easy, but is the expanding the Bernoulli distribution, we obtain the binomial distribution. Let's see the binomial distribution. The binomial distribution has two parameters: the pi that we saw in the Bernoulli before, and the n, which is the number of trials. So it's basically, the binomial distribution is equivalent to running Bernoulli trials several times, in this case 10 times. So the n is the number of Bernoulli trials. And instead of being interested on the probability of success, we are interested in how many successes we expect if we run the Bernoulli trial 10 times. So here we've got range of values from 0 to 10, which are the possible values. If the n equals 10, the possible values is that we can have from 0 successes to 10 successes in 10 trials. Okay, so what you can see is that this is a symmetrical distribution as well. And if the parameter is 0.5, if we change that, then it's not going to be symmetrical. So let's say that the probability of success is 0.8. You are going to see that the distribution peaks on 8, and it's not symmetrical anymore. What is interesting to see is, I'm going to return to the pi of 0.5, but we are going to change the number of trials. Let's say instead of 10, 100 trials. We need to change this to 100 to observe the whole range. And when we observe the whole range, we see this distribution. Now, of course, it's still a discrete distribution because you've got discrete values. But if you keep adding values, discrete values, it becomes closer and closer and closer to a continuous distribution. And if you compare the binomial with the normal distribution, you'll see that they are going to be very similar the more values you add to a binomial distribution. Let's see how many values JASP allows us to add to this. So let's put n 300 and the range to 300 as well. So, and you can see that still got some steps there, but it becomes more and more and more similar to a normal distribution. The beta distribution complements very well with the binomial. Let's go to the beta distribution. So the beta distribution has two parameters, parameter alpha, or sometimes called A, and beta, or sometimes called B. Now, the range of possible values in the beta distribution is from 0 to 1, and so it is a good variable to assign probabilities to probabilities. So the possible values here are 0 to 1, and probability values go from 0 to 1. So how probable is a probability is something that it may sound a bit redundant, but the idea is the following. So remember that we wanted to know, in our examples, we start with a city, which we know the number of people living in each region. So that gives us the probability that a drone will land in that region. So we know the probability of landing in that region. And the binomial distribution tells us is the probability, the Bernoulli distribution tells us is the probability that we land in one region. The binomial tells us if we repeat this, if we observe more than one drone landing, the binomial tells us what's the probability of observing landings in a specific region. Now, in the beta, we do the other way around. What we know is the number of landings we observed, and we want to, based on that, try to estimate what's the proportion of people living in one of the regions. Okay, so if we've got beta A or alpha 1 and beta 1, all the values are equally probable. So the probability that the region, one of the regions, has 50% of the population is the same as that region having 60% of the population, 70%, 80%, 90%, or 100%. So if we add these numbers, we are going to see that. If we add this number, if we use larger numbers here, the values will be closer to 50%. So 2 and 2, it centers in 0.5, but still values that are away from 0.5 are possible. So basically here is telling us we observed 2 landings in one region, in the region of interest, let's say, and 2 landings outside that region. So what's the probability what's the proportion of the population in the region of interest? Well, we don't know. Most likely values close to 50% or 0.5 are more likely, but still values outside, very far from that, are still likely. But if we add more, let's say 20 landings in the region of interest and 20 landings in the region outside the region of interest, well, the probability is still 0.5, and values 0.4, 0.6 are quite likely still. But when you go to 0.3 or 0.7, it's very unlikely, and more than that, more to the extremes, are less likely. And if we have 200 landings in the region of interest and 200 landings in another region, then it becomes closer to 50%. Obviously, if we have different values that are not symmetrical, then this will change. So let's say if we observe 200 landings in the region of interest and only 10 in the region of outside that region of interest, so that means that most of the population lives in the region of interest. So what's the proportion of people living in that population? Well, 0.9 or more. it's more likely than values lower than that. And the opposite is true. So if we have 10 landings in the region of interest and 200 outside that region, so the proportion of people living in the region of interest is more likely to be very low. So let's return to a symmetrical beta distribution, and we can ask JASP to tell us what's the probability to observe values within this range. Of course, if the range of possible values is here from 0 to 1, it has to be any value from 0 to 1. So that's not informative. So, but let's say from 0 to 0.5. So the left side of the distribution. Well, 50% is symmetrical. So if these two, if the values A and B, or alpha and beta, are the same, then the distribution is symmetrical. And so we have 50% of the distribution to one side of 0.5 and 50% of the distribution to the other side. If we want to know what's the probability of the distribution to be between 0.2 and 0.8, then we have that. So basically here between 0.2 and 0.8 is 100% or 1, the probability to be in that interval. So values above 0.8 and below 0.2 are impossible. So the probability of observing values below those numbers is 0. Let's see when we get a non-1 probability for an interval. So let's say we now move to an interval that goes from 0.3 to 0.7. Okay, so in this case, we obtain 93% of the probability is between the values 0.3 and 0.7.